Okay, so today I want to kind of remind us of the connection between the graphs of the derivatives and a few other things with derivatives before we move on into integration. Again, you should have a copy of this. We've written this down at least a couple times this year, and we're going to write it down one more time. But remember that they give you lots of functions. They give you the graph of the first derivative or the graph of the second derivative, and they want you to be able to answer a lot of questions. And so this is just my little way of summarizing it all of these functions. Remember that your critical points of f of x, where your derivative equals 0, are the x-intercepts of the derivative, because those are both the same thing. It's where does f prime of x equal 0. Remember that not every x-intercept on the derivative is necessarily a max or a min. You have to check to see that it changes sign. Your inflection points of your original graph of f of x will be the x-intercepts of your second derivative. And again, because that's where your second derivative is equal to 0. Again, you have to check that it changes sign there in order for it to definitely be an inflection point. And again, just some things I want to make clear to you. Remember, where your function is increasing, it's going to always have a positive slope. Slope is the derivative, so that means we could say that the derivative is above the x-axis, which is another way of saying that the derivative is greater than 0. But above the x-axis on the derivative means increasing, whereas below the x-axis on the derivative means that the original function is decreasing. So where f of x is decreasing is where the derivative is below the x-axis. Sorry, I wish the x-axis here. And that's because that's where your derivative is less than 0. So again, I cannot stress enough to make sure you pay attention when they give you a graph. Is it the function? Is it the derivative, or is it the second derivative on what you're looking for there? We can say the same thing about concavity. Where the original function is concave down, that's the second derivative. So that's where your second derivative is going to be below the x-axis, because that's where the second derivative is less than 0. And where your function is concave up, that means your second derivative is going to be above the x-axis, because that's where your second derivative is greater than 0. And so again, those are the key things they were looking for. We can use the first derivative test, and we can use all that stuff to help us. But a lot of those questions are just coming from the graphs. And then one more thing I want to throw in there is remember that also inflection points and the max and min of the derivative itself kind of go together. So the inflection points of the original function will occur at the max or min of the derivative itself. And again, that's because the inflection points have the possibility of occurring where the second derivative equals 0. And think if you were going to find the max and the min of the derivative. Well, you would take the derivative of the derivative, which would be the second derivative, and you'd set it equal to 0, and you'd solve it to kind of get those critical points. So that's why those are the same, and I think there might be a question or two on one of these tests that you'll see that comes up. So hopefully this will help you on the next test that we're taking. What else can we talk about with derivatives? Well, the mean value theorem is something that comes up a lot, and I think there was a question on the last take-home test you had, and it says, if a function is continuous and differentiable on the closed interval from a to b, then there exists a point C somewhere in between a and b, such that the derivative of c will be equal to f of b minus f of a over b minus a. Remember that that's saying that the slope of the tangent line is equal to the slope of the secant line. We did that little activity after that AP conference that I had last fall, where we practiced seeing like how those would be equal to each other, how the tangent line and the secant line are parallel if it's continuous and differentiable. Because if it's not continuous and not differentiable, that point's not guaranteed. So again, I'm just kind of rephrasing that for you. It says a point C is guaranteed to exist such that the derivative there is equal to the slope of the secant line. Another way to say that is the instantaneous rate of change is equal to the average rate of change, or the instantaneous velocity is equal to the average velocity. And so that comes up every now and again on a free response. I believe there was a multiple choice question on the take-home test, number 1, that just was like, which one of these is guaranteed to be true? And it was basically stating the mean value theorem. Last thing I want to talk about, related rates. Remember that anytime they're talking about the rate of something happening, or you see how much is this changing at such and such time, then you're going to set up a related rates problem. And so I kind of just put an example here. But remember that you want to write the equation or use the equation that's given, that's in this one. You want to look at your constants, like what do they give you? But the big thing on this is we're going to take the derivative with respect to time. So let's kind of look at one of these. It says water is flowing into a spherical tank with a 6-foot radius at a constant rate of 30 pi cubic feet per hour. When the water is h feet deep, the volume of the tank is given by this lovely equation. What is the rate at which the depth of the water in the tank is increasing at the moment the water is 2 feet deep? So notice it says what is the rate. That means it's a related rate problem. Step 1 is you're going to take the derivative. Before I even do that, I'm going to simplify this. You don't have to. We could do the product rule here, but I'm just going to distribute this, and that would be 18 over 3, or 6 pi h squared minus pi h cubed over 3. You with me on that? That way I don't have to do the product rule later. So I'm going to kind of give you some steps on these. So step 1 is write the equation. Sometimes they ask about circumference or area. So you're going to write the equation or use the equation that's given. In this case. And then step 2, we want to take the derivative of that equation with respect to time, because we want to know how fast is it changing with respect to time. So it's kind of like you're doing implicit with respect to time, which means when you take the derivative of every variable, you have to multiply by whatever that variable is with respect to time. So for this equation here, when I take the derivative of v, I'm going to get dv over dt. 6 pi is just a constant, right? I don't have to worry about taking the derivative of that. It's just going to be 6 pi times the derivative of h squared, which is 2h, minus the same thing, pi thirds is a constant, and the derivative of h cubed is 3h squared. And just so you know, this is on a this question comes from a no calculator part of the test. And I could simplify that. I'm going to write this down here so I can move the page up. Simplified, I think I would get, oh my gosh, look what I forgot. What did I forget to do? When you take the derivative of h, you have to do it with respect to time. So every time I took the derivative of h, I should be multiplying by dh over dt. Luckily, I remembered that. Sorry about that. So simplifying that now, I get 12 pi h dh over dt minus, the 3's are going to cancel, pi h squared dh over dt. You agree with that? Step 3, you want to plug in your given values. Probably also not a bad idea here is make sure you know what you're solving for. If I go back up a second, it says I'm trying to find the rate at which the depth of the water is changing or increasing at the moment the water is 2 feet deep. So let's think about what they give me here. 2 feet deep, they don't use d for the depth, they use height. So I think h would be 2 feet. I'm looking for how fast is that changing. So I believe that's what I'm solving for. What other variable do I need? dv over dt. If we go all the way back up here, They tell us the radius is 6 feet, but we don't need that. The radius is constant. The radius isn't even in our formula. But they do tell us that it's flowing in at a rate of 30 pi cubic feet per hour. Cubic feet is volume. So that's our dV over dt. And probably if I was doing this, just to make my life a little easier, I'm going to factor out that dH over dt, because that's what I'm trying to solve for, and just plug it in there. So I get 30 pi equals dH over dt times 12 pi times 2 minus pi times 2 squared. So what's that going to be? 24 pi minus 4 pi, or that's going to be 20 pi dH over dt. So to solve that, I'm going to divide by 20 pi, and I get that dH over dt is 3 halves. And if you wanted to know units on this, think about the units in the height. The height was in feet, and the units on time here, it was 30 pi cubic feet per minute. So this would be 3 halves feet per minute is what that depth is changing, or 1.5 feet per, oh, not minute, sorry, I think it was hours. I'll go back up to the top there. Use the same units there. I believe there's one like this on both the free response from the first take-home test and the, there's a multiple choice question as well. So from that first take-home test, I just want to show you which questions you should be able to go back and look at based on what I've just given you just today. On the multiple choice, 7, 10, 12, 15, 17, 18, 21, 28, 78, 80, 81, 87, 90, and on the free response, I believe number 4, A and B, and number 5, A, B, and C. All of those can be answered using the stuff that I just gave you today. So if you missed those, the smart thing to do would be go back and look at those now and see if using these notes you can figure out what the right answer should be doing that. Okay? So you should have already done some corrections on these. And you should also have another exam that you should be working on as well. All right, so definitely not a bad idea to go back and look at these answers.